Welcome once again, everybody. How are you doing today? Today we want to quickly look at we are still on separation axioms, that is Hausdorff space, or some we call it Tau2 space. And today we'll be looking at some definitions, proof theorems, and some results, and look at one or two examples on Hausdorff space. What does it mean? And before I go to Hausdorff space, I think you can recall that we've explained the concept of Tau0 space and Tau1 space. Now, in Hausdorff space was saying that if you have two pairs, x, y, in topological space x, there are two distinct pairs of y, x. Then we say there is such that x is not equal to y, and remember that there exists what we call open sets, like open sets, such that you have that x is in what, in that open set, and y is not in that open set. Then a space that satisfies this condition is what referred to as what? Tau0 space. I do that they are referred to as what? Tau0 space. Then even for Tau2, you can remember that we have a topological space, you have a topological space, and you have an open set G, a point in that open set G, they call it X, and also you have another point in open set, they call it H, that contain a distinct Y. Then from there, we say that we have your there exists G and H, the open set, such that when you have X in G, Y not in G, and you have what? You have Y in G, in H, then X is not in what? In H. Then when you have short things like this, we said you have what? A Tau1 space. Tau1 space. You can get more details from some of our videos. You can see them, and you learn more. Just go back and learn more about what Tau1 space and what Tau0 space, Tau1 space. Now today we want to look at Tau2 space, or we simply call it Hausdorff space. Now let's look at the definition of this Hausdorff space. Look at the definition of that Hausdorff space. How does it look like? Now, Hausdorff was saying that if you have the topological space, you get it now, and then you have two distinct pairs, usually x in that G, and then you have y in that open set H. You know this now. So, such that whenever you have this, that when you have x is an open set G, then y is open set H, then you cannot say that G intersection H is what? Is an empty set. So that's just a simple definition for what? For Tau2 space. Now let me define it in a way that well clarified definition. Definition. Now we say that a Hausdorff space is a topological space. It's a topological space. I got that. In which you have in which each pair of distinct, each pair of distinct points can be represented or can be separated. By disjoint open what? Disjoint open set. Can show you about disjoint open. I think what I'm trying to say is that, look at this. This is an open set that carry a point x. This is another open set H that carry a point what? Y. Now you can see that both of them are what? They are disjoint. No point of intersection now. So that's why I can say that it is a topological space in which each pair of distinct points can be what? Can be separated. Look at it. Separated by what? Can be separated by disjoint open set. What does it mean? It means that a topological space X is said to be Hausdorff space, or we call it tau2 space. Tau2 space. Excuse me. Or tau2 space now. I got that. So if for any pair x, y in X such that your x is not equal to y, there are two distinct points, so that x is not equal to y, then there exists what? There exists open set, then the G and H in tau, such that you have x in G, then H and then y in H, and implies what? And you have what? G intersection H is an empty set. So when you have this, then guys, when this condition is satisfied, then you can actually say that that topological space is what? Is an Hausdorff space. An Hausdorff space. Are you following now? So that's a simple way for establishing that. Now, before look at this theorem. Look at this theorem now. Okay, that will look at this theorem now. Let me clear this way so that you can have enough time to space to explain this. Look at this theorem now. Look at this theorem. It says that theorem says that theorem, let x be a let me say that every subspace of an Hausdorff space is also what? Is also Hausdorff. Are you getting that? So every subspace of this that you have now is also what? Is also Hausdorff space. Now, like what I said, that if my x is an Hausdorff space, it's an Hausdorff space now. Are you getting that? An Hausdorff space. And then you have your y be a subset of that topological space, be a subspace of that x now. Can we show that this y is what? Is also an Hausdorff what? Hausdorff space. So that is what this result is telling us. This theorem is telling us that okay, if you have a subspace of x, that x is an Hausdorff space, then definitely the subspace of that x must also an Hausdorff space. So that is what this result is trying to tell us. Now, what does it mean? How do we prove it now? Look at it. Because the Hausdorff space now, the Hausdorff space that let's proof. I say that let this x comma tau, let's around x is an Hausdorff space. I'm going to let's be an Hausdorff space, and we all know the definition for Hausdorff space now. And let this x comma tau y, y comma tau y be a subspace. Be a subspace of what? Of this one. I got that. So let's be that you have to make some notation. Okay, let this also be what? A subspace of this. Now, and then because we have two things, we can say that let me pick any two distinct points. Be a subspace of x. I got that with, let us say with what? A not equal to b. I got that because we are looking for can we look for two distinct points in your y? Can we look for two distinct points in y? I got that. When you look for that now, then by hypothesis, because the answer is that it shows that x comma tau x is what? Is Hausdorff. It's an Hausdorff space. So when there was an Hausdorff space now, what happened? By definition now, then there exists open set G and H in tau x. I got that. Shows that you have A in G, then we have what? B in H, and G intersection H is what? Is an empty It's an empty set. So what we are trying to say is that, okay, if we say this x comma tau x is what? Is an ordered space. By definition of ordered space now, in the definition of ordered space, this is what it means now. That okay, if that is a two open set that contain each of the distinct what? Each of the distinct points. That is, now G and A are what? Don't forget that they are what? Distinct, they are distinct set, disjoint sets rather. They are disjoint what? They are disjoint set. Now, since y is a subspace of x, look at it. Since y is a subspace of x, and once y is a subspace of x, you know the definition by a subspace or relative topology now. How do that? Then I can have my what? Open set that will be present in that one. So I will now say y intersection g. I go to that, and what? And h intersection, no, y intersection h, and what? At tau y space. That is, they are what? They are tau y space. We are using the definition of what? Subspace. I use the definition of what? Subspace there. So they are tau y space now. No, tau y open set, because they are, sorry, tau y open what? They are tau y opposite, because they are what? They are by definition of tau naught. You know, remember that when you have a tau y, a set of y intersection g, such that g is what? Is in tau x. So that is where you can say that what? A relative topology, or we call it what? Y is said to be a subspace. Sorry, subspace of that x. Now, since let's look at something. Don't forget that we are picking our x and b, a and b from G. There are two distinct points in that one. So since a is in G, I'll go to that. Then my head what? A is also what? In Y. Look at it. That is, I'm picking x and y from, I'm picking a and b from Y. I go to that. I'm picking a and b from what? Look at it from here. I said let a and b be element in what? In Y. So when you're picking a comma b in Y, definitely a is in G. I go to that because it's part of the open set that we're having now. So a is in G, then b is also in what? Is in H. So a in G, a in Y. Now this implies that my a will also be in what? Y intersection G. Am I communicating now? So the same thing goes for B. B is in G. I know that B is also in what? In Y. Implies B is in what? Y intersection H. Are you considering that? So now there is a condition given us that, note that we have G intersection H is what? It will be empty, but I can now write this guy as because to this implies that I can now write this as Y intersection G. Can you see that? Intersection Y intersection H. Can you see that? So I'll now write this new property of intersection, that is Y intersection what? G intersection H. Can you see that? And we know that G intersection is what? An empty set. So which leads us to Y intersection empty set. I mean, what do you have? You have an empty set. So now this implies that, you know, by rectangles, since these are true, then this implies that Y is an ordered what? Ordered space. It's an ordered space. So that is the way you can show that every subspace of another space is also an ordered space. So that is what we have in that line. I hope you are following now. Now let's look at this example. Let's look at this example. Okay, let's look at this simple example also. Can also assist us and get us what you want to know. Look at this example now. So it's very, very simple. Now what do you need to do here? Now look at this. For instance, so let's look at this simple example now. Okay, let's look at this one first. It says let x, example, let this be a topology on the red line R, as well as the red line generated by open set, by open what? Open closed interval. That is, you have an interval open here and close at this place. I got that. Now, let's just show that this space is what is Hausdorff. So that space is what is Hausdorff. How do we show that? Now, solution. Know something that we have to look for. How do we generate that? We want to show that if I have any two interval here, A and B, in that real number, I know that that's a real number now. Then can I obtain something? Maybe can I obtain so that A is not equal to B? Is it possible to get an open set G that contains A and B and H, so that G intersection H is what? Is empty? Is it possible to obtain that? So that is our draft of what we want to do. Now, what to do, just say that let's start from A, comma B, be what? Be in that it be a real number with A not equal to what? Not equal to B. So if A is not equal to B, there are two possibilities, that is either A is less than B or B is less than A. Now let's assume that A is less than B, and let's say that A is what? Is less than B. Definitely, because they are not equal now. So let's assume that A is less than B. So from this interval now, I want to choose. Let me choose an open set. Let me choose an open set G from that interval. Let's call it A minus 1 comma what? A. Open close. Because that is how my, let me say that I open it like that. And let my H be what? Can you see that now? Also, let me pick my G to be this, and then my H to be what? To be this. Then, from here, by looking at it now, they are both from what? From this topology. I know that they are different topology. That shows that my G and H are what? In that topology that it was getting my open close interval now. So that is taken there. Now, which shows that my A is in what? Is in G. Can you see that? Open close. This my B there. That shows that my A is here. Look at it. Then also B is also in which? In what? In H. You can see that now. B is close there. No. There's a way you can also write it by A minus 1. I mean, let's say A minus 1 comma A. That's what you can write as let's say you pick an X which is less than A minus 1 less than equal to A. Okay, we are now picking the extra part of this one. Let's say you have H with this now. So now, and we have H in G, B is in what? Is in H. Are you got that? Then, and can we have, is there an intersection between, look at it. Can I have A minus 1 comma A intersection open set A comma this one now? Are they related? Now look at from the condition that A and B, they are not what? They are not equal. So are they intersect to each other? No. This implies that my G intersection H is what? Is an empty set. So you can see that the condition are satisfied. Then this space is what? Is Hausdorff. So that space is what? It's an Hausdorff space, because it has satisfied the condition of Hausdorff space. How they are following now? So those are the ways you can actually also prove the Hausdorff space. Now let's look at another example. Another example on this. Look at this example. I was saying that this example was saying that, or let's say a theorem. Let's make it a theorem now. Let's make it a theorem. Let's make it a theorem. What did the theorem say? I was saying that look at this theorem. Now it says that every metric space is Hausdorff. is Hausdorff space. Look at that statement. Every metric space what is Hausdorff space. And then you remember the concept of metric space. Can you remember that one? So every metric space is what is Hausdorff space. What does it mean? It means that let's prove it. Like I said that let x comma d be a what? Be a metric space. Be a metric space. So we can tell as well, let it be what metric, vector of metric space. When you have your d of x comma y is equal to 0, then you have d of x comma y equal to d of what? Y comma x metric. Then transitive, when you have d of x comma z is equal to what? D of x comma z, x comma y, sorry, d of x comma z plus d of what? Y comma x, z comma y. So that is the condition for what? For a d to be a metric space. You can learn more of metric space. Don't worry, can be what we can talk about this. We still talk about more of metric space here. Now, let this be a metric space. For instance, now are you getting that? So when it's a metric space, then we want to show that x is Hausdorff. Then we need to show that x is what? Is Hausdorff. It's an Hausdorff space. I want to show that. Now, to show that now, let x comma y be what in x, so that your x is not equal to y. So let me make it like that. If I pick x and y in x now, I'm picking it from definition. Okay, let me assume that this is not equal to that. Definitely, obviously, you can see that. Obviously, you can show that. Obviously, we can have that my d of x comma y is what? Is not equal to 0. So definitely, if x is equal to y, definitely that will be 0. But here now, it shows that d of x comma y is not equal to 0. That is, we are talking about this talking about this time between x and y is not, they are not 0. That's why I can say that it's obvious that was not equal to 0. So now that let my d of x comma y be what? Let be 2 half. Let be 2 half, which is also what? Greater than 0. I don't know, let be 2 half. So since open space, look at something. Since open space are open sets, they are open what? Open sets a metric space. They are open set what? A metric space now. So open set for this x now, xr of x and what? Xr of y are what? They are open sets in what? In x, such that you can now have you can have my x is in what? Xr of x, and my y is in what? Xr of y. That is, if they are open sets in that space, that metric space, then my point for x with this one, open set for x that you are picking the Dixon point from is this one. The open set you are picking the y from is this one now. I got that. So with this, then it's important to show. You can now show that next target is that we want to show that so we show that xr of x intersects what? Xr of y is what? Is an empty set. So definitely, how do we show this? This is where we need to establish the theorem now. So we're going to show this. The next step, don't forget that we are picking our x is not equal to y. The first part of it is satisfied like that to this. Now, how do we establish this? And we know that x is in what? This open set. Y is in this open set now. So the next step is that to show that this one, the total of the two of them are what? They are empty sets. Right? The two open sets you have in that distance. So how do we establish that? Now suppose by contradiction that x r of x intersects what? X y of r, x r of y is not an empty set. So if they are not an empty set, then there exists what? There exists another opposite z in what? X r of x, it has what? X intersection x r of y. Abi? So when you pick a particular value x from it, because they are not empty, so it implies that my z is in what? X r of x, and z also in what? X r of y. So when you pick it like that, you have it like this, because it is, we assume that they are not empty. That diagonal point that belongs to both of them is in x, also is in y. So after getting this, then by definition of metric, you have this to what? D of x comma z is what? Is less than r, and d of let's say z comma y is also less than r. Am I communicating now? So by triangular inequality, triangle inequality, we have what? What do we have? We are going to obtain d of x comma y, which is less than or equal to d of what? X comma z plus d of z comma y. Are you getting that? So which implies, this one already, we said it's greater than what? 2r. So I'm going to have 2r. This is actually less than, will now be less than r plus r. Are you getting that? So which is what? Less than r plus r, because d of z comma y is less than this, and this is now. Now which implies that 2r is less than 2r. Is it possible? So this is not possible. This is not what? Possible. So once it's not possible now, then our assumption is what? Our assumption what? Fails. Hence, we can only have what? We can only have x r of x intersects what? X r of y, which is what? Which is empty set. Therefore, hence x comma d is what? Is Hausdorff space. Is Hausdorff space. Are you getting now? So that is how you can actually show that every metric space is what? Is an Hausdorff space. You can actually show that every metric space is an Hausdorff space. Very simple as ABC. Every metric space is an Hausdorff space. Are you getting that? So those are the things you can actually obtain. Now, before we go for today, let's look at this result. Let's look at this theorem again. Another theorem is here. Look at this simple theorem. You can actually check it out. Can we show? It said that every tau 2 space, look at this theorem. Every tau 2 space or Hausdorff space, is what? Is a tau 1 space. Wow. Every tau 2 space is a what? Or Hausdorff space is a what? Tau 1 space. What does it? How do we prove it? You know, by definition, proof. You can say that let x be a what? Be a tau 2 space or Hausdorff space. How should let it be like that? Then we show that tau 2 space is what? Is tau 1 space. So that's what we want to do. That. Okay. Now, since our x are Hausdorff space, now what do we need? For let x comma y be what? In x, so that your x is what? Is not equal to y. Abi? Then there exists open sets G and H in this, G and H, such that x in G, y in H, and what? G intersection H is what? Is an empty. So that is the report for the Hausdorff space or tau 2 space. Now, then this also implies that this then obviously we can show that obviously This also implies that x in G, then y is not in G, abi? Then also y in H and x is not in H. Simple as ABC. So when you look at it, it has shown that this shows that X is what? Is Tau space. That is the definition for order space. So that's why I can show that every Tau space is also a Tau space. Likewise, you can also show that every Tau space is also a Tau not space. The same procedure. You just have to assume the definition of that. Same procedure to verify that one. I hope you are following now. Good. Now, okay. I hope you have got this one or two things today. Good. Now, I will leave here for today and we're going to stop for today. And more of it, I will give you examples and you learn more on it also. So thank you very much. Have a lovely time. Okay. Bye bye. I go to school.